So we're taking a deep dive today into V.S. Ramachandran's book, and it's interesting. The English title is The Telltale Brain, kind of hinting at a brain that leaks secrets.
Yeah.
But then our reviewer noticed that the translated title, which is Utodan, translates to The Brain That Tells Stories.
Interesting.
And it got me thinking, are those really so different?
Oh, yeah.
Are the secrets that our brains reveal not essentially stories?
They are, yeah.
Of how we perceive and experience the world?
That's a really fascinating point, and I think it gets to the heart of what this deep dive is going to be about today.
Exactly.
It's not just the stories that our brains kind of conjure up for us, but it's the deeper truths they reveal through these kind of unexpected glitches and the rigorous investigations into those glitches.
Yeah.
And Ramachandran does that so well in his book.
Absolutely. And for everyone tuning in, if you're the kind of person who wants to understand some really complex ideas, but without getting lost in the neurojargon, I think you're in the right place.
Definitely.
We really dug deep into this book to bring you those real aha moments.
We did, and it's amazing the range of topics that Ramachandran goes through in this.
Yeah.
It's astounding.
For sure.
We're going to be talking about everything from phantom limbs, that strange phenomenon, to the intriguing world of synesthesia, where the senses kind of blend together.
Right.
To the really big questions like what makes things beautiful to us, and even how we develop a sense of self.
It's really the whole package deal with this book.
It is.
So consider this your shortcut to understanding the key insights from the Telltale Brain.
That's right.
Without having to read all, 300 plus pages.
The dense neuroscience.
Right.
But we've distilled it into a conversation. Hopefully that's a little bit more approachable.
Exactly.
So to kind of kick things off, I think we should consider the question of what it means to be human.
Okay.
There's been this long debate, hasn't there, about, are we just highly evolved apes, or is there something that sets us apart?
Right. Is there something unique
About it?
Yeah, it's that classic tension.
Yeah.
Like Huxley saying that we're really not so different from chimps, and, Disraeli arguing, no, we're a totally separate creation altogether.
Completely different.
Where does Ramachandran land?
So I think he makes a really compelling case for human uniqueness.
Okay.
And I think to understand his position, you have to think about how the brain itself has evolved.
Right, over vast stretches of time.
Over, millions of years.
It's not like figuring out how a machine works by just taking it apart, is it?
No, it's not a simple reverse engineering problem.
He makes the point that understanding brain evolution is a totally different challenge than, say, Turing cracking the Enigma code.
Exactly, and that's a great analogy.
Yeah.
With the Enigma machine, you could look at how it was structured and figure out how it functioned without knowing its history. But the brain is so deeply tied to its evolutionary past that you can't really understand how it works without understanding how it got there.
Right.
It's about appreciating that long narrative of development.
And that evolution isn't always a straight line.
Oh, definitely not.
Sometimes a part of the brain or even a physical feature, it evolves for one purpose and then gets adapted or co-opted for something entirely different.
Yeah, think about feathers.
Right.
Initially, they were probably for insulation.
Right. Keeping warm.
And then, boom, they become crucial for flight.
Well, flight, exactly.
Or the lungs evolving from swim bladders in fish.
It's really amazing how nature can repurpose things like that.
Yeah.
So Ramachandran suggests that something similar happened with key areas of our brains.
Yeah, he has this idea of a mental phase transition.
A mental phase transition.
And he thinks this might have happened around 150,000 years ago.
Okay, so what was the catalyst for this shift?
Well, the idea is that around that time, certain brain structures and their functions, they kind of underwent this period of rapid change and integration, leading to the emergence of cognitive abilities that seem to be uniquely human.
Okay, so things like
complex language,
okay,
symbolic art, and that sense of self-awareness that we have.
Okay, so it wasn't just a gradual increase,
Right.
It was a sort of qualitative jump.
It was a step change.
So it's kind of like all the basic components were there, but suddenly they clicked together in this new configuration.
A new arrangement.
Creating something far more complex and powerful than just the sum of its parts.
Yeah, think about water turning into steam.
Same molecules, but a completely different state of matter.
Exactly, a relatively small evolutionary nudge leading to a dramatic change in cognitive capacity.
Wow.
And Ramachandran thinks this mental phase transition is a key reason why we are so distinct from other primates.
Fascinating. So let's dive a little deeper into this by looking at chapter 1 of the book,
Okay.
which explores the amazing plasticity of the brain. And he starts off with this really compelling phenomenon, phantom limbs.
Yeah.
So for those who might not be familiar, what exactly does it mean to experience a phantom limb?
Well, it's this phenomenon where individuals who've had a limb amputated continue to have these vivid sensations, often pain, as if the missing limb is still there.
Wow. So you can feel a limb that's not there.
That's right. A persistent experience of something that's physically absent.
That's wild. And for a long time, the explanations for this were kind of all over the place, weren't they?
Oh, yeah, definitely.
There were some pretty far-fetched ideas floating around.
From trauma to mystical explanations, there's a lot of speculation.
But Ramachandran, he approaches it with a neuroscientific lens.
He does. He's a neuroscientist after all.
Yeah, and he recounts this case study of a patient named Victor, whose left arm had been amputated below the elbow.
Yeah, classic case.
And this is where it gets really intriguing for everyone listening. Tell us about what happened when Ramachandran started investigating Victor's phantom limb.
So he did this very careful, systematic study where he would touch different areas of Victor's face and torso with Victor's eyes closed.
Okay.
And he would ask Victor what he felt.
Uh-huh.
And he made this remarkable discovery.
What was that?
That when he touched Victor's left cheek, Victor would report feeling a sensation in his phantom left thumb.
Wow, in his thumb that wasn't there.
Exactly, and then stroking his jaw felt like a sharp object was dragging across his phantom palm.
So it was like his missing arm had been remapped onto his face.
Yes.
That's such a bizarre connection.
It is. It's strange, isn't it?
It really is.
But it actually makes a lot of sense when you consider the physical layout of the somatosensory cortex.
Oh, okay. Explain that.
So the somatosensory cortex, that's the part of your brain that processes touch. And the brain maps for your face and your hand. They're right next to each other.
Okay.
So Ramachandran, he proposed two possible neurological explanations for this remapping.
Okay, so what were the two leading possibilities?
So the first idea was that after the amputation, the nerve fibers from Victor's face, they were no longer receiving input from the missing hand.
Right, because it wasn't there.
So they might have kind of invaded the now inactive hand area of the brain.
Oh, interesting.
Forming new connections and taking over that territory.
So almost like those neurons were getting bored.
Yeah, kind of.
Or looking for something to do.
Yeah, looking for new input.
Okay, what was the other possibility?
The second possibility was that these connections between the face and hand areas, they were already there in Victor's brain.
Interesting.
But they were normally suppressed by the constant signals coming from his real hand.
Okay.
So the amputation would have removed that suppression.
And allowed these kind of dormant connections to become active.
Exactly.
So either way, this was a pretty revolutionary finding, wasn't it?
Oh, yeah, absolutely.
It challenges the idea that the adult brain is fixed.
Yeah, this long-held view that the adult brain was static and unchanging.
But this shows that even in adulthood, these sensory representations can be reorganized.
That's right, they can change and adapt.
And brain imaging studies later confirmed these changes in Victor's brain.
They did.
Which is just amazing.
It really highlights how dynamic and adaptable our brains are, even as we age.
And it wasn't just face and hand connections either, right?
Yeah, you're right.
There were other unexpected sensory overlaps that were discovered.
Yeah, researchers have found cases of a finger map on the face in amputees, and conversely, a face map on the hand.
Really?
In someone who had nerve damage to their face.
It really is amazing how interconnected everything is.
It is. It speaks to the fluid and interconnected nature of the brain's sensory maps.
So you also developed this really ingenious tool to help with phantom limb pain.
I did.
Called the mirror box.
The mirror box.
So how does that work?
Okay, so the mirror box is actually a pretty simple contraption. It's basically a box with a mirror placed vertically inside. And the person with the amputation puts their intact limb on one side of the mirror.
Okay.
And their residual limb on the other side, so the amputated part is hidden from view.
Right.
When they look in the mirror, they see a reflection of their intact limb.
Okay.
Where they would expect to see their missing limb.
So it's kind of creating a visual trick for the brain.
It is a visual illusion.
Okay.
And if the person moves their intact hand, they see the reflection moving.
Right.
And this creates this really powerful illusion that their phantom limb is also moving.
Wow.
And this visual feedback can actually override the brain's learned paralysis.
Learned paralysis.
Of the phantom limb.
Interesting.
Which often leads to a significant reduction in pain.
So you shared the experiences of Jimmy and Ron in the book.
I did.
What happened to them after using the mirror box?
So Jimmy, he described his phantom arm as feeling like a rigid mannequin.
Okay.
And he would suffer from these debilitating spasms.
Yeah.
But after using the mirror box, he experienced immediate relief.
Really?
And for the first time in years, he felt like he could voluntarily move his phantom limb.
Just from looking in the mirror?
Just from that visual feedback.
That's incredible.
It is.
Well, now, Ron.
So Ron, he took a mirror box home,
Mm-hmm.
and he used it consistently for 3 weeks.
Okay.
And his phantom limb and the associated chronic pain completely disappeared.
Wow. Just gone.
Gone.
It's really amazing that a simple visual illusion can have such a profound change.
And other research teams have seen similar results.
So it's not just you who's found this.
No, this has been replicated in multiple studies.
So like who else?
Researchers like Herta Floor and Jack Tao, they've independently replicated these findings.
Providing strong evidence for the effectiveness of this mirror visual feedback in treating phantom limb pain.
That's right. And Jack Tao's study even included a placebo group.
Okay.
Where they used a sham mirror, and the real mirror box showed significantly better outcomes.
So it really does seem to be the visual feedback.
It really does.
That's making the difference.
It's pretty remarkable.
And the applications of this mirror visual feedback, they extend beyond phantom limbs, don't they?
They do.
You mentioned its use in stroke rehabilitation.
Yes.
And for a condition called complex regional pain syndrome?
That's right, CRPS type 2.
Okay, so how does the mirror box help with stroke rehabilitation?
So for stroke patients who have experienced paralysis, the mirror box can be used to improve movement and sensation in the affected limb.
Interesting.
By providing visual feedback of movement through the reflection of the unaffected limb.
Okay, so they're looking at their good limb.
Yeah.
And it's tricking their brain into thinking that their paralyzed limb is moving.
Exactly, and it can help to reactivate those neural pathways.
Wow.
And for complex regional pain syndrome type 2, which is a chronic pain condition, often triggered by a relatively minor injury.
Yeah.
The concept of learned pain is really relevant here.
Learned pain, what does that mean?
So the idea is that after an initial injury, the brain can sometimes learn to associate movement of the affected limb with pain.
Okay.
Even after the initial tissue damage has healed.
Interesting. So it's like a feedback loop.
It is a vicious cycle.
So the brain is anticipating pain.
Yes.
Even though there's no reason for it anymore.
Exactly. And the mirror box can help to unlearn this association.
By providing visual feedback of pain-free movement?
That's the idea. And studies have shown positive results in treating CRPS too.
Wow. So it's really promising.
It is a really promising therapy.
You also described an experiment with a concave lens in a patient named Chuck.
Yes, I did.
Which further demonstrates the influence of visual input on perceived pain.
So in this experiment, Chuck was looking at the reflection of his intact arm through a concave lens, which made the image of his phantom limb look smaller.
So his brain is seeing a smaller limb.
Exactly.
Interesting.
And what was really fascinating was that he actually experienced a decrease in the intensity of his phantom limb pain.
Wow. Just from seeing a smaller image.
It's remarkable, isn't it?
It really is.
And it raises the question of whether visually altering a real limb could have a similar impact on real pain.
That's a really interesting thought.
Yeah, it's a fascinating avenue for future research.
So all of this points to a fundamental shift in our understanding of the brain, doesn't it?
It does.
We're moving away from this idea of a static, hardwired organ to recognizing its incredible adaptability.
Yes, we're coming to understand the brain as this dynamic system that's constantly rewiring itself in response to our experiences.
So are these phenomena of lifelong plasticity and phantom limbs unique to humans?
Well, not entirely. Other animals exhibit brain plasticity and can experience something akin to phantom limbs. But Ramachandran argues that the degree of lifelong plasticity we see in humans is a core aspect of our uniqueness. It's our capacity to use learning and cultural transmission to drive changes throughout our lives.
That really sets us apart.
Exactly. He even introduces this concept of homo plasticus to emphasize this.
Homo plasticus, I like
The adaptable human.
And where does neoteny fit into this picture?
Neoteny. That's our extended period of childhood.
Right.
It's absolutely crucial. This prolonged immaturity allows for a much longer window of brain plasticity.
Okay.
It gives us more time to absorb information, learn complex skills, and shape our adult minds through experience.
So it's like we're born with this incredible potential, and our extended childhood gives us the time to develop it.
Exactly.
That's fascinating. So Chapter 1 also takes an interesting detour to explore the origin of humor.
Oh, yeah.
Which might seem unrelated, but Ramachandran connects it really well.
He does. He uses it as an example of how our brains process unexpected events and resolve incongruities.
So he contrasts human laughter, especially at cognitive humor, with what appears to be laughter in apes.
Right.
Which seems to be triggered by physical interactions like tickling. So what is this false alarm theory of humor that he puts forward?
So the false alarm theory suggests that humor arises when we initially perceive something as being wrong or threatening, but then quickly realize that it's actually harmless.
So give me an example.
Think of someone slipping on a banana peel.
Okay, classic.
If they're seriously injured, it's not funny.
Right.
But if they get up unharmed, the sudden unexpected fall,
followed
by the realization of no real danger, often elicits laughter.
Right, so it's that relief.
It is the relief from a false alarm.
It's like, oh, thank goodness they're okay.
Yeah.
That's funny.
Exactly.
So how does this connect to the case of Mickey laughing at pain that you mentioned in the book?
So Ramachandran suggests that in Mickey's case, who laughed when experiencing pain, there might be a disruption in the normal processing of pain signals.
Okay, so the pain signal is getting mixed up?
In a way, yes.
It's interesting.
The insula, which registers pain sensation, sends a signal.
Okay.
But the anterior cingulate cortex,
Which is involved in?
which processes the emotional response to pain,
Okay.
doesn't get the expected danger message.
So it's like the brain is saying, hey, this is painful.
Yeah.
But wait a minute, there's no real threat here.
That's the idea.
Yeah.
The brain misinterprets the pain signal as a false alarm.
And that leads to laughter.
Yeah, the incongruous response of laughter.
That's so strange.
It's fascinating.
It really is.
And he applies the same logic to tickling.
Okay, so why do we laugh when we're tickled?
Because it's a situation where you're being physically manipulated,
Okay.
which could be perceived as a potential threat. But it turns out to be playful and gentle.
Right.
So again, resolving that false expectation of danger.
So he's suggesting that our more complex forms of humor might have evolved from this basic mechanism.
Exactly, from this fundamental neural mechanism of resolving false threats.
He even touches on the human smile as a related phenomenon.
It's fascinating, isn't it?
It is.
So the baring of teeth in primates is often a sign of aggression.
Right.
But in social interactions, this aggressive display can be inhibited or modified, and it evolves into a signal of appeasement and friendliness.
Okay, so like a non-threatening smile.
Exactly. It's like a half-hearted grimace that says, I'm not a threat.
So the potential for aggression is averted.
Yes.
Much like the resolution of a false alarm in humor.
That's right.
Fascinating. Okay, let's shift gears now and move on to Chapter 2.
All right.
The many maps of vision.
Okay.
While we share the basic structure of eyes with many animals, the way our brains process visual information is remarkably sophisticated, isn't it?
It really is. The basic anatomy of the eye isn't that unique to humans.
Right.
But the complexity of visual processing in our brains is exceptional.
So how is it different?
Well, humans have a lot more visual processing areas in the brain.
Okay.
We have around 30, compared to many other mammals, which typically have around 12.
So more than double.
Yeah, more than double the visual processing power.
Wow. And this expansion is closely tied to our evolutionary history, right?
Absolutely. So our distant ancestors were nocturnal insectivores,
Okay.
living in the dark, eating insects.
Makes sense.
But as primates, transitioned to a diurnal lifestyle.
So daytime living.
Yeah.
Okay.
The need for complex visual motor abilities became paramount.
So things like...
Accurately grasping branches, twigs, leaves,
Okay.
coupled with the development of color vision.
So we could see those ripe fruits.
Exactly, those brightly colored fruits and nutritious foliage.
So all of this created a need for a more elaborate visual system.
It did.
Yeah.
Yeah, there was a lot of evolutionary pressure to develop a better visual system.
You also mentioned a rather memorable aside about the potential evolutionary roots of kissing.
Oh, yes.
And you even linked it to oral sex.
I did.
That was quite a thought.
It was a bit of a tangent, I'll admit.
But an interesting one.
I thought so.
So you speculate that our attraction to lips might be a vestige of our fruit-eating ancestry.
Yeah, where visual cues like the redness and fullness of fruit
Right.
signaled ripeness and nutritional value.
Okay.
And he extends this to suggest that human kissing and oral sex could be a repurposing of these ancient drives.
So we're attracted to lips because they remind us of fruit.
It's a playful speculation.
It is a funny way to think about how evolution might have influenced our behavior.
It is a humorous take on it.
Okay, so the dexterity of the human hand also played a role in shaping our visual and visuomotor brain regions.
Oh, absolutely. The fine motor skills enabled by our hands,
Yeah.
and especially our opposable thumbs,
Right.
they exerted a significant pressure on the development of brain areas dedicated to visually guiding these precise movements.
So we needed to be able to see what we were doing.
Exactly. We needed that visual feedback to manipulate objects with precision.
Right.
Just think about all the things we can do with our hands.
It's incredible the things that we take for granted.
It is,
You know, just picking up a pen,
Or threading a needle.
things that other animals just can't do.
That's right.
So you also introduced this concept of canonical neurons in the book.
Yes, these fascinating neurons.
And they're located in the frontal lobe.
That's right.
And they blur the lines between perceiving an action and actually performing it.
So what's interesting about canonical neurons
Okay.
is that they fire not only when we do something like grasping an object,
Uh-huh.
but also when we simply observe that object.
So just looking at something can activate the same neurons
That's
as
right.
actually using it.
Yes.
That's a really deep connection between perception and action.
It is. It suggests that our brains aren't always making a clear separation between seeing and doing.
Wow.
It's like the potential for action is always present in our perception.
And human visual perception, it's evolved beyond just basic object recognition, hasn't it?
It has. We've moved into the realm of symbolic meaning and the ability to manipulate visual symbols in our minds.
Right. So we can imagine things
Exactly.
that don't exist.
We can create mental images of things that aren't physically present.
Like mythical creatures.
Yes, like unicorns and dragons.
Or even just, everyday objects in different arrangements.
That's right. We can imagine a chair turned upside down.
Even though we're not looking at an upside-down chair.
Exactly.
And Ramachandran proposes that this ability might have paved the way for language.
He does. He suggests that this manipulation of visual symbols is a precursor to language.
That's fascinating.
It suggests that our visual imagination is deeply connected to our ability to communicate.
To illustrate how deeply ingrained these evolutionary memories are in our brains,
Mm-hmm.
you highlighted the case of John's appendicitis diagnosis.
Oh, yes. Dr. McPhee's brilliant diagnosis.
So how does that connect to our discussion of vision and brain maps?
So John's case is a great example of how our brains retain an evolutionary blueprint of our bodily development.
Okay.
So the initial pain from appendicitis is often felt around the belly button, even though the appendix is located in the lower right abdomen.
So the pain is in the wrong place.
In a way, yes.
Interesting. So why is that?
Well, it's because in the early embryo, the appendix actually develops near the umbilicus.
Near the belly button.
Yes.
Okay.
And it only migrates to its final position later in development.
Interesting.
So our brains seem to remember this original location.
Even though the appendix has moved.
Yeah, it's fascinating, isn't it?
It really is.
And the progression of John's pain and the other clinical signs that Dr. McPhee observed, they also tell a story rooted in our biology.
Okay, so
The way the pain shifts to the lower right quadrant as the inflammation progresses,
right.
and the phenomenon of rebound tenderness.
Rebound tenderness.
That's that sharp pain when pressure is suddenly released.
Yeah.
Those are all direct consequences of the anatomical location and the inflammation affecting the appendix.
So these seemingly subtle signs, they provide clues about what's happening inside the body.
They do. They give us a window into the underlying biology.
And how our brains interpret those signals.
Exactly. Our perception of pain is shaped by these deep-seated biological patterns.
It's amazing how much information is hidden in those subtle signs.
It's like our bodies are speaking to us in this ancient language.
A language that we're just beginning to understand.
That's right.
So as we wrap up this deep dive, what are the key insights from Ramachandran's book?
Okay, so I think the first key takeaway is the brain's remarkable plasticity.
Its ability to adapt.
Yes, its ongoing ability to reorganize and adapt throughout our lives.
So our brains are constantly changing.
They are, yeah, they're not fixed and static.
Okay, what's the second key takeaway?
The second is that our evolutionary journey has shaped our cognitive abilities.
In unique ways.
Yes, in ways that make us distinctly human.
Building on older brain structures.
That's right, taking those older structures and repurposing them for new functions.
It's really quite remarkable.
It is. It's a testament to the ingenuity of evolution.
Okay, and what's the final takeaway?
The final takeaway is that studying unusual neurological cases,
Those telltale brains.
Exactly.
can offer us incredible insights
They give us a glimpse into the workings of the normal brain.
and help us understand what makes us unique.
That's right.
It really reinforces the idea that we are not just slightly more advanced apes.
No, we're not just apes. Plus,
Right.
we have these extraordinary capabilities
That have emerged through evolution.
and through our lifelong adaptability.
So for everyone listening, this raises a question.
Okay.
If our brains are so adaptable, what other hidden potentials might we be able to unlock
What other capabilities are lying dormant within us?
as our understanding of these mechanisms deepens?
That's a great question to ponder.
It is. It's a question that I think Ramachandran's book really makes us think about.
It does.
So thank you for taking this deep dive with us today.
It's been a pleasure.
And we encourage you to keep pondering the secrets that our amazing brains might hold.
There are many more mysteries to uncover.
For sure.